Good morning, guys. Here we are. We are here for the lecture number 3. And this lecture number 3, let me just put in a presentation mode. The PowerPoint presentation is related to the radiation laws. You remember that in the first two lectures, and especially in the second part of the first lecture, I introduced a general schema that is related to all the different steps of the remote sensing process, starting with the external source of electromagnetic energy, that is the sun, passing through the interaction of this electromagnetic energy with the atmosphere and then with the Earth surface and then back to the detectors of the sensor mounted on board of the satellite and then the interpretation of the data. I mentioned the facts that this schema is very important in order to fully understand which are the different steps that we need to learn in order to have all the information necessary for the remote sensing acquisition phase. But in the second lecture, I will introduce all the topics related to electromagnetic spectrum, and so I didn't go through that schema. And also in these third lectures, unfortunately, I cannot going through the topics related, for example, to the point A of the schema, that is the external source of electromagnetic radiation, because we need to introduce another thing. And this other things is related to the radiation laws, because before talking about how and what kind of energy our external source of energy, that is the sun, is emitting energy, of course we need to better understand that's behind the terms of emission. And so we need to introduce this concept related to the radiation laws. So let's start with this presentation. And when we are talking about radiation laws, and maybe it's something that you are already familiar because it's coming from the essential of physics and mathematics, but we will recap for what we need in remote sensing of these different laws. These fundamental laws of radiation that affect the quantitative aspect of remote sensing techniques are in our case only 4. But of capital importance. For their determination, the most eminent European scientists of the last century were involved. Which are these 4 different laws? The first law, and this is the most important laws, it's named Planck's law, which describes the trend of the power emitted by the surfaces as a function of the wavelength and their temperature. The second one is the Stefan Bosman Law, which provides the total amount of power emitted by the surfaces calculated over the whole electromagnetic spectrum as a function of the temperature. So I mean the Stefan Bosman Law is a sort of generalization of the first one, that is the Planck's law. The third one is the Wien law, or law of displacement, which indicates the value of a wavelength where the electromagnetic emission is maximum for a certain temperature. The fourth one, that is one law that is very important for the remote sensing process, is the Kirchhoff's law, which established the relationship between the absorption coefficient alpha and the emission coefficient epsilon. All right, now we are going through these 4 different laws with some different figures in order to understand which is the importance of these different radiation laws. So, before mentioning all these laws, you have to know that these laws were more or less all formalized at the beginning of the 20th century, especially in 1900, because there were a sort of research competition launched by the German Academy of Science. And so this is one of the reasons, because most part of these radiation laws were formalized by German-speaking scientists, because the announcement of this sort of research contest was in German, and so only the German were able to participate. But of course, also the German School of Physicists was at that time very strong, and so many of the groups came from Germany itself, or from Austria, or for other German-speaking countries. So what we need to introduce is that before speaking about all the different four laws, that it is known that any natural surface that is placed at a temperature that is higher than the absolute zero, here you see that the absolute zero is equal to minus more than 270 degrees Celsius. So I mean, whatever, and therefore practically the whole physical world that's surrounding us, if all the bodies, all the surfaces are in this condition, and of course everything that we have on the Earth's surface is in that condition, that means that the surfaces emit electromagnetic radiations on the whole spectrum. The quantity and type of radiation emitted by these surfaces, by these targets, by these things that we have, for example, over the Earth's surface, and of course in the sun, depend on the temperature, T, here, and on the nature of the surfaces of the body itself. And this certain sort of emissivity is regulated by the emissivity coefficient epsilon that we will introduce later on. And this emissivity coefficient epsilon, which expresses the ease with which a given surface emits electromagnetic energy. So, there are in fact surfaces that emit energy more easily than others, and which, at the same time, hold back even more easily radiation. These surfaces and are therefore strong absorbers, and also at the same time very strong emitters or radiators. The surface of the body that is emitting energy is a radiator. So we can have surfaces that being very strong absorbers of energy, that means that are absorbing all the energy that is striking over this surface, over this body, could be at the same time very strong emitters, and being the emission, as we will see later on, based on temperature, at the same time a body could absorb energy and emit energy in the same time. When this condition is taken to the extreme, we are in presence of the so-called black bodies. What are the black bodies? The black bodies are bodies that are able to absorb all the energy and they emit as a radiator the maximum quantity of energy. That means they are perfect radiators. All right, the characteristics of a black body, therefore, is that, as I mentioned, of having an ideal surface such that for each given temperature T, it emits the maximum possible amount of electromagnetic energy, that is, with maximum efficiency over the entire spectrum, and at the same time it is able to totally absorb the incident electromagnetic energy, whatever the wavelength. So in this case, the black body emits the maximum possible amount of electromagnetic energy over the entire spectrum, so it absorbs energy, whatever the wavelengths. And in the same time, a black body totally absorbs the incident electromagnetic energy, again, whatever the wavelength. All right. I'm sorry, I need to go on with the presentation. Okay, in this way, the excitance M, you remember that we introduced the excitance M in the previous lecture, the lecture number two, when we introduced the concept of radiometry. So the excitance M of a black body is equivalent only to the value of the emittance, being the incident energy totally absorbed, and therefore there is not any reflection. This is not easy to understand, but I mean, you can understand that thinking about the facts that if you have a black body that is absorbing all the energy by definition, that means that there's no reflection, all right? So whenever you don't have a black body, so another kind of body that is not able to absorb all the energy, when we are measuring the energy emitted by this body, that it depends from the temperature T, we will measure not only the energy that this body is emitting, but also the fractional part of the energy that is not completely absorbed and then that is reflected. But this is true for real body, not for black body, because for the black body, the reflection is null. All right. A black body surface, or more simply what we call black body, is imaginable as the surface of a small opening with respect to the surface of a large isothermal real cavity. And here you have the figure of this black body. I'm sorry, it's in Italian, but I took this figure from the original book that was first translated in Italian by Planck, that is related to these to his laws, to the definition of his laws. So I mean, it's a very ancient and it's a very typical representation. So you have to imagine that this black body is could be for having a black body could be used what is called a cavity, a radiant cavity, this one on the left part of the figures, where you see you have this cavity. In particular, here we have a section of this cavity where there's a very small opening here, the A point, that connecting the inner surface of the cavity to the external environment. So that means that with respect to the surface of a large isothermal real cavity, this one, whose internal walls, I mean the internal surface that here is circular. So in these figures we assume that the 3D figures is a sphere or an ellipsoid, will do not completely reflect the radiation. So we are here introducing for the first time this letter. This letter is not P, but is a Greek letter that we will mention and we will fully explain after a few slides. It's called rho, that is the reflection coefficient. So that means that when you have incident radiation here that is coming in through the cavity from these little openings that we have here, this energy, being this cavity not really a black body, but something that is going to simulate a black body, that means that being not a black body, this inner surface is not absorbing all the energy, all right? So part of this energy will be reflected in other direction, like here. And you see that if the opening is very small, the energy that was incident before will exit after a while, I mean after many different reflection inside the cavity. That means that after a while, when this energy will exit, will have no power at all, because at every single incidence, part of this energy is absorbed and part is reflected. So having so many different paths of reflection, when exiting here, the energy will have no power. All right? So why they were using these things here that is called cavity, a radiant cavity? Let's read the next slide. If the entrance hole is small enough with respect to the size of the cavity, as I mentioned before, it's very unlikely that the trapped energy for a kind of pot effect will soon find a way out, and therefore comes out only after large number of reflection, of course, extremely damped. At this point, the surface of the entrance hole is to be considered black and is able to absorb all the incident radiation regardless of their wavelength and angle of incidence. For example, in this case, for a sphere, if this section of the figure before is representing in 3D, as I mentioned before, a sphere, for example, the ratio between the depth of the cavity and its opening must not be less than 10, while the minimum number of necessary internal reflection in order to exit is at least 10. So after 10 reflection, the energy that is exiting for this very small hole is completely with no power. All right, but why they use this cavity? I mean, they use this cavity because in order to establish the radiation laws, all the different groups, scientific groups, during this research contest, they suddenly realize that if you want to establish a general expression related to an emission law, you should perform many different experimental tests, because in reality you have an infinite kind of different bodies, and every different bodies is emitting energy in a different way. So, for example, just considering a white wall is reflecting energy, and being over the absolute zero temperature, of course, will emit energy. But at the same time, for example, a lamp is emitting energy because it's warm, it's hot, and so it will emit maybe more energy than our wall. So you have to think about that in the real world we have an infinite kinds of different surfaces that are emitting energy. while at the same time, pure black body, are not present on the Earth's surface. Because it's something that is ideal. It's not a real body. But apart from that, all the scientific groups realized that in order to establish a formalized laws, they needed to perform a large number of experimental tests with registering the emission. And having infinite different bodies in the real world, the result is, of course, that in order to generalize from the analytical point of view an emission law, you need to perform infinite measurements. So the only way to solve this problem, and they realized that suddenly, was why do not use a black body? And then, if we will succeed in order to formalize a general emission law for a black body, then we will have the task to generalize to all the other bodies. But as mentioned before, black bodies are not present in the real world, and so they use this radiant cavity in order to simulate this black body. So, from an emissive point of view, it is observed that the surface of the hull of the cavity emits a radiation that does not depend on the direction of emission, but only on its temperature T. A black body surface, or more commonly black body, is therefore a perfect radiator and is usually useful as a reference standard. As I mentioned a few minutes ago, it is an ideal surface that actually exists only with a good approximation, as can be seen from the previous figure. Real surfaces with great emissive capacity are generally spectral radiators, and that is their ability to resemble an ideal black bodies only holds for certain wavelength intervals. So that means that, we have no black bodies on the real world. There are an infinite quantity of different other bodies that sometimes could resemble to a black body, but only for a very small range of wavelengths, not for the entire electromagnetic spectra. So all these scientists think about to simulate this black body using that radiant cavity. The figures that I showed you before was something that was real. Was a monolithic block of rocks or heavy metals where they dig a cavity inside, and then they try to put energy in the very small hole that connected the inner cavity with the external environment, and then have a spectrometer, an instrument that is able to collect single measurements in single wavelengths. They measure at a certain temperature the emission of energy in this radiant cavity that was simulating the black body. So, you see, you have these spectral radiators, and we are going to the same things here. I'm sorry, there are some problem, okay? So, they call that spectral radiator, and radiant cavity, this simulated bodies, this cavity, they were simulating the black body, and all the other bodies, the real bodies, are defined gray body. So a gray body is defined as a body whose mgg, that is the emission, the emittance of a gray body, so the excitance, is always lower than that of a black body M of equal temperature and with the same emissive behavior at all the wavelengths. So I mean, they defined at the same time the fact that there's a black body and all what is not black body. So all the real bodies are called grade. And if we take as a reference the emittance M of a black body surface at a certain temperature T, and mcg, that is the emittance of a gray body surface at the same temperature T, we define an emissivity coefficient epsilon using this ratio. So now we are introducing one of our five, let's say four in reality, four very important coefficients that we are using in remote sensing. The first one is the emission coefficient epsilon, that is simply the ratio between the excitance of a gray body, that is a real body, divided by the excitance of a black body that is simulated with the radiant cavity. Being these two bodies, the real body, the gray body, and the black body, being at the same temperature. All right? So, from this definition, it can be deduced that for a black body surface, epsilon is of course equal to 1. If you have a black body, epsilon is equal to 1. While for any other surface, epsilon is less than 1, of course. It's equal to 1 only for black bodies. So that means that epsilon is a coefficient that is ranging between 0 and 1, and is 1 again only for the black body, and is less than 1 for any other real body. All right, let me check if the recording is still active, otherwise I'm wasting my time. Let me check. All right, we spend at least half an hour for this part. All right, so I'm going back to the presentation. So, concerning real and black body surfaces, this is the 7th slide. Furthermore, as mentioned above, the actual surfaces show an emissivity values that varies with the wavelength. So the previous equation must be written in general terms such as these things here. So I mean the epsilon, the emission coefficient, is a function of lambda, of wavelengths, and so it's equal to the ratio between the emittance of a gray body in the different wavelengths divided by the emittance of a black body in that particular wavelength or range of wavelengths, again having these two real body and black body at the same temperature during the measurement. So there are two very important things that are valid for this coefficient, for the emission coefficient. But you will see when we'll introduce the Kirchhoff's law that this is true also for the other three coefficients that we will take into account, that this coefficient and the other three are coefficients. So again, are ranging between 0 and 1, but all these coefficients, and of course also epsilon, the emission coefficient, is function of wavelengths, of lambda. So that means that it's not constant with the ranging of wavelengths. And we can understand these things here just if you have a look to these figures. It's again in Italian, but I mentioned before that I took that from a physics compendium at the beginning of the 20th century. So you see here we have again a b-dimensional diagram, where again you see here, as I mentioned in the second lecture, on the x-axis we have wavelengths. Here they are measured in microns, and you see, just to get familiar with the spectral bands, here we have the 0.4, 0.8. That means that you remember from 0.4 to 0.7 we are in the visible, and here 0.8 is around the near infrared. This is not extended to all the wavelengths, because you have to be aware that the spectrometers that the different German-speaking scientific groups used at that times were sensitive only to this very small range of wavelengths, in particular before 0.4, and in particular in the ultraviolet, till to the near infrared. This is a common situation. The only exception, and that was great for him, was the group of Planck that were used a spectrometer that was sensitive also to a very small portion of the mid-infrared. And using these spectrometers, it will succeed in generalize the form of the radiation law, or the general radiation law. And you see in this diagram, so again, as I mentioned before, the variation of the emittance of the energy that is emitted, and you see here you have the spectral emittance, that is the excitance M. You see here measured in watt per square meter and microns. You see here from 0 to at least 2000. I mean, you see here there are three different curves. This one, this here, is related here, you see in Italian, is corpo grigio, is a gray body. Here is a real body, the bold one, while the dotted one is a black body. So you see here, they all these different groups, they take some measurement with spectrometers using, for example, three different bodies. A black body is not real in reality. There's no in reality, so they use a radiant cavity in order to simulate that. Then they use a gray body, something a very common surface. And here, for example, just for let you know these things here, this real body that is expressed here was a lamps, an electric lamps with tungsten filaments in there. And so you see, they understood a very important things, and we can also understand these things just having a look to these figures. So that means that the energy that is emitted from a real body or from a black body is depending on the wavelengths, and is not constant with the wavelengths. That means that it's not a line that is parallel to the x-axis, of course. And you see that being all these three different bodies at the same temperature, of course, in order to be compared each other, that means that apart from the temperature, because it's the same, you see that a black body is emitting more energy in comparison with the other, and is emitting more energy for every single wavelength. So in 0.4, that is the beginning of the blue band, the black body is emitting more than the real body, and in comparison with a gray body, a generic gray body. And of course also in 0.6, that is the starting of the red band and so on, and also in the near infrared. So the black body is emitting more energy with the same temperature of other bodies in every single wavelength, but you see that if I'm calculating the integral of these different curves, so that is the area behind all these different curves, that means that the total quantity that the black body is emitting in comparison with a gray body is bigger, of course. So that means that the black body is emitting more energy wavelengths by wavelengths, but also in range of wavelengths. So if we are integrating these curves between 0.4 to 0.7 in the visible, for example, the black body will emit a larger amount of quantity in comparison with the gray body. All right, so in the first case, with epsilon equal to 1, because this is a black body, we have the ideal black body situation. In the second case, the one with epsilon that is less than 1 and constant over the whole emission spectrum, the curve represents a typical gray body, while in the last case, we have an example of a curve that represents a real surface where the emissivity, epsilon lambda, varies with the wavelengths remaining always less than 1, of course, because it's not a black body. It may happen, and this is written in bold, that a surface, so it's very important, a surface behaves differently along the spectrum, very close to a black body for certain intervals of wavelengths, or for gray body in others, and of real body in others. So that means, and I want just to introduce these terms, there are surfaces that we can detect, we can imagine using sensor mounted on board of satellites that could be very similar to black bodies in part of the electromagnetic spectrum. So, for example, water in the infrared, especially in the mid-infrared, is a very, very good absorber of energy. So, for example, water, if observed in the mid-infrared by satellites, so very far, is very similar to a black body because it's absorbing all the energy that is striking, being this energy in the mid-infrared emitted by the sun. So in the mid-infrared, for example, the water is a very good absorber. It's very similar to a black body. All right, so we introduced the concept of radiation body, and so we can go into the Planck's law. Okay, what is the Planck's law? The general law of electromagnetic emission was enunciated by the physicist Max Planck in December 1900, after tens of years of discussions and disputes between the greatest scientists of the time. The many more years passed before this law was completely verified and then accepted. So I mean, this law was accepted after many, many years because, in the same time, they were refining all the sensor in order to acquire electromagnetic energy, and then after some years, it was completely accepted. This law is fundamental as it describes in quantitative terms the ways in which electromagnetic energy is produced, a phenomenon that applies to every surface above, as we mentioned before, the absolute zero. In practice, in our case, in our real world, for all physical surfaces. Planck's law allows to calculate by units of surface area and wavelength lambda the spectral flux density m lambda emitted by any body by means of the following expression. Don't panic, this is the expression. You see, I don't want you to learn that by heart, but if you can, it's better. And you see, this is the general Planck emission law. You see that you see here lambda. That means that we are calculating the emissivity here in lambda. So that means that is ranging, of course. It is changing over the electromagnetic spectrum. But in this case, you can calculate the Planck's law for a specific lambda. What are all the different things here? You see that h, that is here, is called the Planck constant, and this is the unit of measurements. C is, that you can see here, is the speed of light in vacuum, as we mentioned also in the first lecture. K, that is somewhere here, you see, is what is called the Boltzmann constant. Of course, lambda are the wavelength. T, capital T, that is here, is that is measured in Kelvin, is the temperature, and the epsilon lambda here is the surface emissivity, as calculated with the ratio that we introduced before. So epsilon lambda is the emission coefficient for this particular wavelength. All right? So let's take into consideration in a very practical way this equation. You see that apart of what we are going to calculate, this quantity here, we know that epsilon lambda can be calculated just having for every single particular surface a coefficient, an emission coefficient in different wavelengths, so it's something that is known. Let's check what are the different things. This is all this quantity here, you see, are constant or are known, and the also see here h, they are all constant. The only things that are not constant, you see here, are lambda and t, capital T. So all these different things here, there are only two unknowns, and the unknowns are lambda and T, the temperature. So wavelengths and temperature. Taking into consideration that we already mentioned the facts that the phenomena of the emission, that is this quantity here, is of course ranging in the different wavelengths, you see here. That means that being m a variation of lambda, the only unknown here is the temperature. All right? So let's go on here. And given the presence, as I mentioned, of some constants, the relationship can be rewritten in a simpler form, such as this one. So we have these things here, and I mean, here you see it's very simple, and you have only two different constants, C1 and C2, and you see C1 is these things here, and C2 is these things here. So I mean, we can rewrite the equation, the Planck's equation, in this way. And so now it's very clear that being C1 and C2 two constants, again, being the emission a function of lambda, the only variable of the system, the only unknown, is the temperature, capital T. All right? So the graphical representation of Planck's law, parametric with respect to the temperature and the wavelengths or frequency, is the trend that we can see in these figures here. All right? So again here, a bidimensional diagram. You see on the x-axis we have wavelengths. Here they are ranging from 0 to around 3 microns, so we are getting familiar with the spectral bands. So, I mean, we are ranging between the gamma rays, X-rays, ultraviolet, the visible here, you see, that has also the colors. Then we have the infrared, and then we are going till to 3 microns. That means that we are in the middle of the mid-infrared. And you see here on the y-axis, we have the spectral radiance, so the M value. So you see here, these are 3 different curves, and well, there are actually there are 4 curves, and you see with different colors, red, green, blue, and black. So that means that this diagram, as it was mentioned before, is parametric with respect to the temperature. So we have the representation of the function of the Planck laws for the same body having this body at a different temperature. All right? So let's take into consideration 3000 Kelvin, 4000 and 5000 Kelvin, and you see that, having the same body, you can simply understand here that, higher is the temperature, higher will be the emission. And not only for every single wavelength, as I mentioned before, but for all the wavelengths we are taking into consideration. So if we are calculating the integer, for example, between 0 and 3 microns, you will see that for the blue curve, and it's very easy to get it, the area that is subtle, these curves, is bigger than the one under 4000 and 3000, of course. So that means that a body, a real body or a black body is the same, is emitting energy, and this emission is directly proportional to the temperature of this body. What is quite amazing, according to me, to these laws, is that, of course, real bodies, so the Earth surface or the Sun, is not emitting the same quantity of energy for the different wavelengths. So the emission is not a line parallel to the x-axis, but has this particular shape in which you have a point here for very small wavelengths, and the wavelengths will be smaller with the increase of the temperature, where there's an activation of the emission, then a peak of emission here, the maximum, and then you see that for larger wavelengths, the emission is going to be asymptotic. So that means that, for example, you see this is the blue curve, so it's very similar to the emission of electromagnetic energy by the sun. You see that the maximum of emission by the sun is in the visible, and going for larger wavelengths, you see here, for example, in the mid-infrared, or for example in the radio bands, as I mentioned in the lecture number 2, the sun is emitting a very low quantity of energy. You see here is asymptotic. It tends to be 0 for longer wavelengths. All right? So let's go on. So to know the power emitted by the surface of any body in a certain range of wavelengths, it is sufficient to integrate the previous equation in the chosen interval. So the resulting expression is this one. So if you want to generalize that in order to understand how much energy, for example, is emitted by the sun in a range of quantity lambda 1, in a range of wavelengths comprised between lambda 1 and lambda 2, and for example, we want to understand how much energy is emitting the sun in the visible, we can calculate this emissivity between 0.4 to 0.7 microns using as temperature the temperature, as we will see in the next lecture, of the sun, that is approximately ranging from 5,000 to 6,000 degrees Kelvin, and we can understand how much energy is emitting the sun. That is very important, of course, in our case. You can understand that, because in order to understand how our Earth's surfaces are reflecting energy, we need to know how much energy is emitted by the sun. All right? So, if the emissivity is constant, the emittance will depend exclusively on the wavelength lambda and the temperature T, as we mentioned before in the other slides. All right, so this is the Planck law. You see, some is not difficult at all. I mean, you have only to have some particular attention to the general disclosure of this particular law. So now we are going to Stefan Bosman Law. That is very simple. In order to know the overall emittance M of a physical surface on the whole electromagnetic spectrum, it is enough, of course, as you know, to integrate Planck's law on all the wavelengths of the electromagnetic spectrum, from 0 to infinity, of course. I mean, so, leaving aside the development of the integrals, that is very difficult, so I don't want to explain that to all of you, because I mean, we are really interested in the results of the calculation of this integral. You see, I'm sorry, I'm again pressing the wrong button of my mouse. You see that if we are taking the emittance M and we are integrating that from 0 to infinite, the quantity, I mean the Planck's law, the results is, I'm really embarrassed of that, it's really simple, because the results is equal to epsilon times sigma times the 4 powers of the temperature. And you see here, sigma is a constant, all right? So I mean, if we want to calculate the emittance of a black body or of a real body, you can use simply this equation, where you are multiplying this constant sigma to the 4th power of the temperature, that is the temperature in which that body that you are performing the calculation is based, and then you have to multiply that with epsilon times epsilon. That means the emission coefficient, all right? So, of course, if we are calculating a black body, epsilon will be equal to 1. For all the other cases where epsilon is less than 1, of course we are calculating the total emission in the whole electromagnetic spectra for a gray body. So that means that the Stefan Bosman law is valid for all kind of bodies. Because, why that? Because there's embedded in the equation, it's embedded epsilon. As I mentioned before, 1 for black body, less than 1 for all the other bodies. So, here you have written down these things here, and you see that for real bodies, where in fact the emissivity is changing with the wavelengths, the previous equation must be rewritten in this form here. You see, for real body, for gray bodies, so what we are, for example, for the surfaces that we can find over the Earth's surface, I mean the epsilon, the emission coefficient, you remember, from the diagram we saw before, is not constant for all the wavelengths. So that means that when calculating the Stefan Bosman laws for a real body, for a gray body, we can take out from the integrals sigma and temperature, and having for every single wavelength recalculating, and we need to recalculate the epsilon that is ranging in the different wavelengths. It's a sort of complication, but of course it's due if we are considering real body. And you see again, MCR indicates the emittance of a real body. So, just concluding the Stefan Bosman's law, you see here in this very bright diagram, again, this is the case in which on the x-axis we don't have wavelengths, but you see here we have temperature, we have no units of measurements, and in the y-axis we have the emittance M. You see that, the curve, it's an hyperbola, you see here, because, it's the fourth power of the temperature. So when the temperature is increasing, of course, also the emittance is really increasing. And you see here, these are the bodies, as again a parametric representation of the Planck laws for bodies that are in different temperature condition, and this is what you can get from the Stefan Bosman law. All right, so we finish also the second law, so we are only missing two of the laws, but the Wien's law is very simply, because another extremely useful law in remote sensing is that stated by Wien in 1893, so before the Planck's law. It says that the wavelengths, that is the maximum wavelengths of emittance corresponding to the maximum electromagnetic emission of a black body surface, decrease with increasing the temperature T, according with this ratio. So this things is very simple. So that means that using the Planck law, you can calculate the maximum of emission using this simple ratio. So the maximum wavelengths, the wavelengths of the maximum emission is the ratio between this constant here, that is 2898, divided by the temperature of the body in which you want to calculate the wavelengths of the maximum emission. And this quantity here comes out in microns. All right? So, considering the temperature, of course, I'm going back, the temperature here expressed in Kelvin degrees. All right? So, let's go to the second slide of the Wien laws. It's clear that this function, as you can see here, has the shape of a branch of hyperbola. You see here we have again the same diagram, again the x-axis wavelengths, here ranging from around the visible to the far infrared, so the thermal infrared, the beginning of the thermal infrared. Here you have the spectral radiant excitance, and here you have a parametric curves that are the same body with this body at different placed at different temperature. You see here the temperature is around 600 degrees Kelvin. Here it is almost 900, here 1000, here 1200, and so on. So you see that using the Wien laws, you can calculate the peak of emission. And you see that if you are connecting in this parametric representation of the same bodies placed at different temperature, if you are connecting all the maximum points calculated with the Planck laws, you have a branch of an hyperbola. So that means that increasing the temperature, that means that the maximum wavelengths of the maximum emittance will go towards smaller wavelengths. So bigger is the temperature, smaller will be the wavelength. Lower, and on the contrary, will be the temperature here, bigger will be the wavelengths of the maximum emission. All right? So, this is quite important, I'm sorry, because I have to mention these things here. Let's go back. You see, what about the wavelengths of maximum emission of our two reference bodies? For example, the Sun and the Earth's surface. I mentioned, and we will see in the next lecture, that the Sun has a temperature that is ranging between 5,000 to 6,000. That means that if we are dividing this quantity, for example, divided by 6,000, the result is around 0.5 microns. So that means that the Sun is emitting in the visible with a maximum emission in the visible. In reality, the maximum quantity of energy, as we will see in the next lecture, of the Sun is placed in 0.55 microns, that in the visible, these 0.55 microns, corresponds to a particular color. And you all know which color is that. I don't say right now, because we will see that in the next lecture. For the Earth, you have to know that if we are calculating the mean value of the temperature of the Earth's surface, the temperature is around 250, something like that, degrees Kelvin, right? So you see that using these Wien laws, the results is around 10.5 microns. So that means that the Earth is emitting with a maximum in the thermal infrared. And this is very important, and we also see that in the next lecture. All right, now we are going to conclude this very tough lecture. We are concluding that just mentioning what is very important for us, but trust me, and you will see it's very easy, the Kirchhoff's law. The Kirchhoff's laws is taking into consideration that although the phenomena of interaction of electromagnetic radiation with surfaces deserve a more in-depth discussion, the specific object of the next chapter, it is important to present the aspect of energy balance that involves the study of such interaction. So we need in some way to understand which is the energy balance in our real case, and especially if connected to the remote sensing techniques. So when electromagnetic radiation strikes any surface, three different interaction mechanisms are possible. The first is that part of the incident radiant flux, that is phi, the incident flux. So the first mechanism of interaction, as you all know, is the reflection. So part of this incident flux, phi, is reflected, and this quantity is called phi, flux reflected. A part could be absorbed, and we call this quantity phi A, standing for flux absorbed, and finally the remainder of the whole incident radiant flux could be transmitted, and we call this transmission, this transmitted flux, phi t. For the principle and for the general principle of energy conservation, then we have this relationship. So that means that the sum of the fluxes, of the three different fluxes, the reflected one, this one, the absorbed one, and the transmitted one, will be equal to the incident radiant flux. So that means that all the energy could be reconverted in one of these three quantities, of course. Nothing is added and nothing is lost, of course. And this is the principle of energy conservation. So if we are taking into consideration this general principle of energy conservation, we can do a very simple thing. For example, we can normalize these three quantities with respect to the incident energy phi I, obtaining thus these three quantities. So we can normalize all these reflected, absorbed, and transmitted fluxes. We can divide it, so normalize, for the incident flux. So it's quite obvious that every single element, for example, the ratio between the reflected flux phi r divided by the incident flux phi I, is of course comprised between 0 and 1. And the sum of these three quantities is of course equal to 1. This is another way to express the general principle of energy conservation. But which is the best things for us? It's just having normalized, having these three relationships with respect to the incident flow, strictly depends on the physical nature of the surfaces and the roughness characteristics, and can be defined as, pay attention, because they are the three different other coefficients we need in remote sensing. So we can have the ratio between the reflected flux phi r divided by the incident flux phi is called rho, and rho is the name of the letter that stands for the reflectance coefficient. The ratio between the absorbed flux divided by the incident flux is called alpha, and this alpha stands for absorptivity coefficient, while the third coefficient, that is called tau, here you see it is equal to the ratio between the transmitted flux phi t divided by the incident flux phi I, is called transmissivity coefficient. So, recapping, we have rho, that is the reflectance coefficient, alpha, that is the absorptivity coefficient, and tau, that is the transmissivity coefficient. And I remind you that we have introduced just a few minutes ago also the other fourth important coefficient we need in remote sensing, that is the epsilon. You know, you remember the emission coefficient, that is the ratio between the energy, the emittance of a gray body divided by the emittance of the black body, being these two bodies at the same temperature. So these are very important coefficients, and of course we can again rewrite the general principle of energy conservation in this way. So stating that rho plus alpha plus tau, of course, is equal to 1. And what we can add that alpha, rho, and tau, of course, are coefficient adimensional coefficients. That means that are ranging between 0 to 1, and these three coefficients are ranging according to the chemical physical nature of the surfaces and according to the degree of roughness or polishing. For example, if we are don't take into consideration this example that is right down here because it's not very clear, but is taking into consideration, for example, a glass of our window. I mean, a glass of our window in the visible will be characterized by a very high transmission coefficient. So, for example, a glass of a window will have in the visible for 0.4 to 0.7 microns a tau that is very similar to 1, because the task of the windows is just to be bypassed by visible energy in order to illuminate, for example, our rooms. That means that stating the general conservation energy conservation principle, if you have a tau that is equal to 1, that means that in the visible, the glass of a windows is not reflecting, because the rho will be, of course, nearly similar to 0, and is not absorbing energy, because I mean the sum should be equal to 1. In another case, for example, think about a mirror. A mirror is characterized by definition as a perfect reflector, so that means that the rho coefficient, the reflection coefficient, will be very similar to 1. And if the rho coefficient, the reflection coefficient is very similar to 1, that means that taking into consideration this equation, that is the general principle of energy conservation, if rho is nearly 1, that means that for a mirror in the visible again, the absorption A alpha and the transmission tau will be equal to 0. All right? Very, very simple. So in cases where even the reflected energy is almost 0, as happens for black bodies, for example, the relationship is simplified in the following. So I mean, and we will demonstrate that later on, when we will introduce the concept related to the interaction between the electromagnetic energy and the surface. We will demonstrate that epsilon is equal to alpha and is equal to 1 for black body. So that means that for a black body, by definition, of course the emission coefficient is equal to 1, and being a perfect absorber, also alpha is equal to 1. That means that for all the wavelengths, a black body has a rho, a reflection coefficient, and a transmission coefficient equal to 0, which is another way of expressing Kirchhoff's law and summarized one of the fundamental concepts of radiation physics, which is essential in defining ideal black body surfaces. This relationship indicates how in general surfaces that absorbs a lot, emit a lot, and reflect little, of course. All right, so let's see the very last slides. It should, however, be noted that for real surfaces which are neither black bodies or nor gray bodies, it is always necessary to take into account the dependence of their specific coefficients on the wavelengths. So again, all these three coefficients, alpha, tau, and rho, are functions of wavelengths. And so they are ranging with different wavelengths. So remembering therefore the definition of the emissivity coefficient, the general equation becomes this one. So you see that being this ratio equal to the epsilon, to the emission coefficient, that means that if you want to For example, expressing the absorption coefficient. The absorption coefficient will be the complementary with respect to 1, so the rho coefficient subtracted to the quantity 1. All right? In this case, you can take these things here. So, in order to better understand the relationship between black bodies and real bodies and their basic interactions, imagine a natural surface. Whatever place is an ambient with a temperature of almost 300 Kelvin degrees. As it's intuitive, this surface will be subject to a series of interactions, and the radiative process can be summarized as follows. So, the surface naturally emits electromagnetic energy, of course, has a temperature that is over the absolute zero, and the surface will emit energy in accordance with Planck's law and in relation to this specific capacity of spectral emissivity that is the epsilon lambda. So the emission coefficient that is arranging with wavelengths. Second things, based on its absolute temperature T and the Wien law, the maximum value of its emittance spectrum will be around 10 microns if we are considering 300 degrees Kelvin. You remember the Wien laws. And so the maximum of emission will replace around 10 microns wavelength. More precisely, for 300, in 9.66 microns, then in the thermal infrared region. Third things, in other neighboring bodies are in turn, the other neighboring bodies, I mean the other bodies that are in the Earth's surface, that are surrounding our target, are in turn, of course, almost all sources of energy, both as natural radiators and as reflectors with respect to the energy coming from other sources. So when we are considering our energy, we cannot, our body, I mean our surface, we cannot considering this surface as the only surface, but there will be other surfaces, and our surfaces in which we are interested, for example, acquiring some images over that, will interact with the other surrounding surfaces. So we need to consider also these interactions. Last things, the surface is affected by these irradiance flows, as may show different consequent behaviors in terms of absorption, transmission, and reflection. This is the direct consequence of the third point, that having other surrounding bodies, our target surface will interact in terms of reflection, absorption, and transmission with the fact that all the other bodies, being real bodies, all the other surfaces, being real surfaces, and having a temperature that is over the absolute zero, will be emit energy, of course. So I mean, in our real world, we need to consider all the surfaces like a system that is interacting. All right, this is the end of a very tough third lecture, so we will meet with the fourth one that will take into consideration the point A of the general schema I have introduced. That is, I remember you, the external source of energy. Thanks a lot.